Hello, I'll wait for some time in case somebody wants to join. Maybe 5, 10 minutes, I'll start the class. Okay, so to begin today's class, we will first give an overview of the atomic absorption spectrometer layout, okay? Before we move to the individual components. So first, there is the radiation source, the hollow cathode lamp that we talked about in previous classes. It generates element-specific radiation, which corresponds to the resonance line of the annihilate atom. Okay. This light corresponds to the resonance line, that is the first excited state of the annihilate atom. Annihilate atom. So this hollow cathode lamp is the radiation source. Moving forward, we have the flame or the atomizer. Again, I explained like it can have flame mode or it can have furnace mode. So basically, for instance, if you have groundwater with some pollutant like arsenic, it will be in the form of a liquid, right? So that liquid sample is put in a flame, and because of the temperature, it is converted into free atoms, right? So basically, the atomizer it plays the key role of providing a steady population of atoms for absorption. What's the next step? The monochromator. After the radiation passes through the flame, the monochromator isolates the desired wavelength from other background light, ensuring selectivity. Lambda is the wavelength. Next step is what we know as detector. It measures the reduced intensity of radiation after absorption by the atoms in the flame. Finally, we have amplifier and readout. So from the name, you can guess what they do. What does amplifier mean? So basically, it amplifies the signal, right? You know amplitude, right? So yeah, it basically amplifies the signal, which is displayed as an output. And readout means like you are reading the output. So this allows quantitative analysis of the element's concentration. So basically, what is this is amplification of signal, the electronic signal, okay, output display. This allows quantitative analysis of the element's concentration. So if I were to summarize this in one line, I will say that radiation from the source passes through the atomized sample in the flame where free atoms absorb at specific wavelengths, and this absorption forms the analytical signal. Okay, so this is the layout of the AAS. So moving to the next part. What is the next part? It is nebulizer and atomization. So basically, what the nebulizer does is that it converts the liquid sample into a fine spray or aerosol, and that is further put in the flame where it is atomized. Okay, so that's the function. So basically, this you need not know, but I'm just giving you information that there is a very thin plastic capillary. It draws liquid from the sample flask into the nebulizer where it encounters fuel gas and oxidant. Fuel gas like acetylene and oxidant that can be air or oxygen. And then the liquid is dispersed into fine droplets. So around 20% of the liquid becomes the spray suitable for atomization. The rest form larger droplets discarded as waste. Okay, so because of this limited efficiency, it necessitates a waste collection. The flow rate is typically 2 to 5 ml per minute. If too much flame enters, the flame can be extinguished. So precise control is necessary to ensure flame stability. I'll write it in terms of watts. There is a very thin plastic capillary of the order of say hundreds of microns. At capillary, Ross liquid from this from sample flask into nebulizer. So in the nebulizer, it encounters fuel, acetylene, and oxidant like air or oxygen. Okay, and the liquid is dispersed into fine droplets. So around 20% of the liquid becomes spray, which is suitable for atomization. And the remaining 80% is just waste. It's discarded because they are in the form of larger droplets. Okay, basically it's in the form of large droplets. The flow rate is typically 2 to 5 ml per minute. If too much liquid enters, the flame can be extinguished. So that is something that you have to be aware of. If too much liquid enters, flame can be extinguished. So keep that in mind. Precise control is necessary. Okay. So what are the types of burner systems? So first is a premix burner. Maybe I won't go too much into detail, but I will explain. And if you want, you can refer to it in the net or ask ChatGPT. So in premix burner, the fuel and oxidant are premixed before reaching the burner head. So as the name implies, pre means what? Before. So before reaching the burner head itself, the fuel and oxidant are mixed. It produces a laminar flame with controlled temperature and droplet distribution. So it's a laminar flame. So advantage is low turbulence. It's very stable flame and then reduced noise in signal. The disadvantage is that it is susceptible to clogging if solids are present in the sample, potential explosion hazard if not handled properly, and atomization efficiency is 10 to 15%. Okay. The other type of burner is total combustion burner. So from the name, what can you tell about it? So it's not premixed, okay. In this case, the fuel and oxidant meet directly at the burner head, so there is no premixing involved. It handles samples with higher solid contents. There is less risk of clogging. Okay. The disadvantage is that you have less control over the flame. Okay. So it can be unstable. Both these burner types are used quite often. The choice depends on the nature of the sample and the analytical requirements. For instance, if you feel like in your sample there can be higher solid content, you should go for total combustion burning. Okay. And you should go for premix burner if you want like reduced noise in your signal, a stable flame, etc. So what are the fuel oxidant combinations and flame temperatures? And just go to the next point. Okay. So what is the first thing? Natural gas plus air. So this produces a low flame temperature, 1700 to 1900 degrees. Okay. You can have natural gas plus oxygen. Here, slightly increased flame temperature, 2700 to 2800 degrees Celsius. Okay, but it requires higher fuel consumption for efficient burning. Then you can have hydrogen plus air. This with this you can achieve 2000 to 2100 degrees Celsius. You can have hydrogen plus oxygen. So obviously a little bit more, 2300 to 2500 degrees Celsius. You can have air plus acetylene. Okay, so it's the most commonly used combination. It's the most commonly used fuel oxidant combo. Okay, so with this you reach 2100 to 2400 degrees Celsius. So why this is most used is that it has got very stable performance. Okay, you can have acetylene plus nitrous oxide. This gives you 2600 to 2800 degrees Celsius. So this is more suitable for refractory materials analysis. Refractory elements like chromium, aluminum, etc. Okay, can also have acetylene plus oxygen, and this provides a temperature around 3000 degrees Celsius, very high temperature. Okay, but handling is a bit more tricky. So there are a number of choices as you can see. The choice of fuel oxidant pair dictates flame temperature, atomization efficiency, and suitability for different types of elements. So next, moving on to flame structure in AS. So basically, there are three zones. Okay, primary combustion zone, interzone, and secondary combustion zone. So I'll just write them down. Primary combustion zone. So in this case, it is at the base of the flame. It's a blue region, okay? Blue region at base of flame. And over here, there is incomplete combustion. Second is the interzonal region. This is the greenish region in the middle. Okay, it provides the richest source of free atoms. Fine. So this makes it the most useful zone for measurements. Third part is secondary combustion. So, so this is the red region at the top. Okay, so the first one was at the base. This is at the top. The speciality of this region is that complete combustion takes place over here. Okay, so the interzone is a part like which provides the richest source of free atoms. So that is most important for us. So I'll just make that note, an important note for reproducible and sensitive measurements. What is most important for us is the interzonal region. Okay, so basically the nebulizer is very central to the AS because it produces aerosols, but again the efficiency is a bit less. I told you around 20% only. And then there is the burner type where we saw like there is premix burner or total combustion burner. Premix burners are more controlled but hazardous. Combustion burners are robust but noisy. Then we looked at various fuel oxidant combinations which influence the flame characteristics. And I told you that air acetylene is a standard one, while acetylene and N2O, that is nitrous oxide, is used for refractory elements. And I also talked about the flame zones and choosing the correct region, that is the interzonal region, is critical for sensitive detection. Okay, so yeah, let us move on to flame structure. So basically today in this class, like we will be covering more about flames. It's all just theory, theory, theory. Okay, there is no big equation or numerical here. Yeah, okay. Maybe take a 5 minutes break and then we will listen. Okay, so just to recap, uh, The flame has got three distinct zones: the primary combustion zone, the interzonal region, and the secondary combustion zone. Primary combustion zone is the one which is blue in color. Okay, and over here there is not enough oxygen for complete combustion. So there is blue color over here due to the band emission of C2, CH, and other radicals. I mean, these things you don't need to know much. But what you have to know is that this is not of analytical interest. Okay, the interzonal region height is about 1 to 3 centimeter depending on the flow rate. This is a zone which contains free atoms and stable molecular oxides. This is the most useful region for atomic absorption since free atoms are required for measurement, and the burner height is adjusted so that the hollow cathode lamp radiation passes through this region. Okay, so I'll just write it in form of notes. The interzonal part region, like interzonal region, it's the most important one for our analysis. So I'll just write this one extra point is that burner height is adjusted so that hollow cathode lamp radiation passes through this region. The secondary combustion zone is the upper part of the flame, and over here there is complete combustion, but this is not useful for analysis. Okay, so the flame temperature profile is such that uh, the temperature distribution depends the height above the burner. Near the orifice, it's like 1700 to 1800 degrees Celsius. Around 3.5 centimeter above the flame, it is 1830 to 1863 degrees Celsius. So that's the maximum temperature zone. And the sides of the flame have got lower temperature than at the center. The key point is that the hollow cathode lamp radiation should pass to the hottest part for maximum efficiency. Okay. So the flame absorption profile also varies with the flame height. It again depends on the element that you want to analyze. Like if you want to detect magnesium, the absorbance increases with height, peaks at around 2 centimeter, and decreases beyond 4 centimeter. But in case of a refractory element like chromium, the maximum absorbance is near 1 centimeter and then decreases sharply as the temperature falls. So these things already Sir has covered, so I'm not just going. You can just refer to his notes, class lectures again. Uh, the burner height adjustment, like that adjustment is allowed by most AS instruments. There is around 1 to 3 centimeter adjustment. Correct adjustment you need for maximum absorbance. Okay. So common flames also I told you, like air acetylene flame, which is the most common in AS. Okay. So that is suitable for most elements except the refractory ones. Okay. Just write this in notes perhaps. Acetylene is I think C2H2. The acetylene is C2H2. So the air C2H2 flame, this is most common in AS. Okay. It's suitable for most elements except refractory ones. It also has got some limitations. Okay. For instance, alkali metals like sodium, potassium, lithium, they ionize at these temperatures and the absorption signal is very weak. So they are operated under slightly oxidizing conditions. That is, you take excess air. Okay. On the other hand, if you take excess fuel gas, you'll get a reducing flame, and that is more useful for alkaline earth metals like calcium, barium, magnesium, strontium. For them, you use reducing flame, and yeah, and even noble metals can also be analyzed using air acetylene flame. So there are some exceptions like aluminium. It forms Al2O3 particles in the form of goblets in the flame. Okay, it's sort of free ions it produces Al2O3 particles, so they don't atomize effectively. And as you know, that atomization is very important to measure the signal. So for aluminium, the signal is very weak. Okay, it's a drawback. So like that, for magnesium, oh god, for magnesium, for chromium, okay, uh, the absorbance peaks at particular flame height. Okay, for instance, for magnesium, the absorbance increases with increase in flame height, peaking around 2 centimeter, and beyond which it decreases. For chromium, which is a refractory element, maximum absorbance is at 1 centimeter height. Okay, so these examples you can refer. Absorbance का variation with height. Variance is like a statistical term, so I'll just put variation with height. Okay, so I already told you about alkali metals and noble metals, alkaline earth metals. Okay, so basically the position of the flame zone relative to hollow cathode lamp is very, very important. Okay, so what are the key takeaways here? So one is that position of flame zone relative to hollow cathode lamp is very important. Okay. Next takeaway is that the interzonal region is the most important when it comes to analysis. And why is it most important? Because it contains maximum free atoms. Okay, the middle part of the flame. Thing is that most AS equipment has got this burner height adjustment. Okay, okay, so this is a very key optimization parameter. For maximum absorbance. Okay, I already told you about the air acetylene flame, but it is not suitable for alkali metals due to ionization. And I also told that alkaline earth metals they require a reducing flame. Then we saw some case examples like aluminum, magnesium, chromium, etc. How they behave in the flame and how the operational conditions must be optimized. Let's move on to the next part. So, like as we already saw that the flame acts as the absorption cell. Okay, think of the flame as absorption cell, where the radiation from the hollow cathode lamp passes through. Okay. That flame only it has got combustion zone, primary combustion zone, secondary combustion zone, interzonal region, and optimal temperature. Okay, for the various elements also. And the flame height adjustment I already told you it can be done. Air acetylene flame very common, except for the refractory elements like chromium. Let us look at nitrous oxide acetylene flame. I think nitrous oxide formula is N2O. Nitrous oxide C2H2 flame. Yep, N2O. N2C2H2 flame, it provides higher temperature, roughly around 3000 degrees Celsius. So slightly excess fuel gas also. So it has a reddish flame. Okay. So basically it's a reducing zone. So the advantage in this case is that it reduces oxides of refractory elements. But the disadvantage is that at very high temperature there is increased ionization, thus lowering the sensitivity. Okay. So that's the nitrous oxide acetylene flame. And why is it used? It is used, we already talked about it earlier, that it is very suitable for refractory elements. Okay. So if you want to detect refractory elements, you can't go for the acetylene flame, but you have to go for nitrous oxide. Not acetylene air, but nitrous oxide acetylene. Okay. So another thing that is important is that atomic absorption, it requires very sharp resonance lengths. But in case of nitrous oxide acetylene flame, there is a very strong broadband emission from CN, CH, NH radicals. Okay, so these radicals emit very broad bands overlapping with the resonance lines. So you have a lot of background absorption, affecting the precision of the instrument. Okay, so that's a disadvantage in this case. What about gas flow? So gas flow rate is very critical. Okay, if you have very low flow, there can be flashback. What does the meaning of flashback mean? It means flame sucked into burner, increasing the chance of explosion. If there is high flow, the problem is that the flame can blow off burner. So we need very proper adjustment, very precise adjustment to ensure stable flame. Stable flame, you have to adjust. So what's the atomization mechanism in flame is? See, I already told you that atomization is the most critical step. Okay, as only ground state free atoms produce useful absorption. So what are the steps? First is nebulization and aerosol formation. Okay, so the sample solution is nebulized into fine droplets. Larger droplets are removed, smaller droplets enter the flame. Next stop is for desolvation. So in this case, the water or the solvent around ions evaporate and the droplet shrinks, leaving behind solid salt particles. After that comes volatilization. Okay, so the solid salt particles evaporate or volatilize into gaseous molecules. And after that comes dissociation. Each of these has got subtopics like nebulization. I can expand that. Nebulized into fine droplets. The larger droplets are removed as waste. Okay, likewise for dissolution, the water is evaporated, droplet strings leaving behind the solids. But I'm not going into all that details, so I'm just writing the main points. So in dissociation, what happens is that the gaseous molecules break into the free metal atoms. Okay, and there can be competing side reactions also occurring. Okay, but that is not useful for AS. Next is the atomic absorption step. So in this case, what happens is that you have some uh, free metal atom. say M in the gaseous form, it gets converted into M star G, M star. Okay, so the star denotes excited state. So from ground state to excited state in the gaseous form, it happens. Okay, so that's the atomic absorption step. Basically, the ground state metal atoms absorb radiation from the hollow cathode lamp, giving rise to sharp resonance lines. There can be other emission processes also. Okay, okay. Those are the side reactions, but these are not important for our detection. Like there can be a lot of side reactions, many equilibria, but the analytical signal in AS arises only from the free ground state atoms absorbing lamp radiation. So maximizing that concentration is the main purpose for our optimization process. Okay. Let's take a 5 minutes break. After that, we'll proceed. Okay. So we already talked about the types of flames, right? Turbulent flow burner as well as the premix burner. The turbulent flow burner is just the total consumption burner or the direct injection burner. So yeah, I'll just tell that if you come across turbulent flow burner or direct injection burner, just note that they are same as total consumption burner. So in turbulent flow burner, basically what happens is that the fuel gas and oxidant supporting gas do not premix until they reach the flame, and the liquid sample solution is converted to aerosol and sprayed directly into this mixing zone. And since all this spray enters the flame, the system is known as total consumption burner. Okay, there are other details like it's very tall flame, narrow flame. All of the liquid sample enters the flame, short, light path, etc., etc. No need to do all that. So imagine throwing a handful of wet sand into campfire. Okay, some of that grains will vaporize quickly, but others will pass without burning fully. So this is similar to how some droplets escape atomization in turbulent burners. And in premix burner, we already discussed it in detail earlier, that the gases are mixed with the sample aerosol before entering the flame. Okay. So what are the burner design considerations? Burners are usually made from titanium, stainless steel, or other non-corrosive materials. To reduce salt buildup, the burner tip has got multiple small holes or slots. Okay. So there is something called long tube technique, where the flame is directed into a quartz or ceramic tube to increase the optical path length, greatly improving sensitivity. However, this technique is unsuitable for refractory oxides like chromium, tungsten, vanadium, etc., which do not atomize easily. They are best suited for elements like cadmium, zinc, and noble metals. Okay, now moving on to flame geometry. The light beam from the hollow cathode lamp must pass entirely through the flame. Okay, and longer the path, higher the sensitivity. Turbulent flow burners provide only a short path, reducing sensitivity compared to premix burners. Okay, all this and all okay, fine. Optical components already told you about the concept of resonance lines, why we use monochromators, etc. The optical path is like from hollow cathode lamp to flame to entrance slit to the prism or grating to the exit slit to the detector. Okay, I'm just checking from source notes whether what is relevant to explain what is not. Okay, let us come to the optics part now. Hmm. Sorry. So what do we need to know about optics in AS? We need to know about monochromator. So basically monochromator is an optical device used to select a particular wavelength of light from a mixture of many wavelengths. We generally use Cherney-Turner monochromator. Okay. We generally use Cherney-Turner monochromator. Okay. Filter-based monochromators cannot be used in AS because the resolution is too poor. So the lenses mirrors are generally made of quartz or fused silica. Okay. The term monochromator is slightly misleading because it never produces a truly single wavelength of light, but always a small band of wavelengths. The job is to select a resonance line and reject unwanted background or other lines. If background radiation passes through, the calibration curve becomes curved instead of straight. Okay. So the next part is wavelength selection. So for alkali metals like sodium, potassium, you can use simple glass-based filters because their lines are in the visible region. So for most other metals, their absorption lines are the UV region. So you have to use interference filters. Okay, coming to detectors. It collects the light after it passes through the monochromator. It usually has detector, example photomultiplier tube, power supplies, amplifiers, and readout devices. Okay. Earlier, like we used to have analog meters, but in modern systems, they use digital displays, and computers can store, calculate, and print results. Okay, so we generally mostly see photomultiplier tubes. Okay, so the next part comes signal quality and instrumentation types. Okay, because why this is important is that flame fluctuations can add unwanted noise. So we use amplifier locking at a specific modulation frequency so that only the desired signal is strengthened, reducing the noise. And here also the instrument types, uh, single beam and double beam instruments. You can just Google about it and see what they are. I've not put the diagrams. So take it as your homework and try to find them. Then of course the next part is the optical pathways, readouts and computers. Before that you also have amplifiers to amplify the signal. Okay. Readouts basically the computers display the concentration directly. Calibration curve, statistical analysis, concentration values are all automatically calculated and stored. But the operator's role is important because even with all the automation, The user cannot blindly accept the data. Okay, he must understand the machine and check the results. So yeah, the computers basically store the calibration curves, compare results, perform error analysis, etc. There are automatic samplers in the instrument, and the computer functions basically range from adjusting the gas flow rate for a stable flame, controlling the flame lighting and stick fit, and moving the burner head automatically when changing gases. They also store element specific data and run background corrections, interference corrections, standard additions, etc. So the first automatic analyzer came in 1966, but modern instruments can hold several hollow cathode ray tubes, lamps in a rotating turret. They automatically change lamps, adjust slits, optimize optics, etc. And they allow simultaneous multi-element analysis. Okay. So the key takeaway basically here is that, yeah, monochromators are essential for high resolution. Filters alone are not sufficient for alkali metals. Double beam instruments, single beam instruments, all that I asked you to see as homework. Photomultiplied tubes are the main detectors. Okay. Two diode arrays are sometimes used for multi-element analysis. And I talked about automation of computers, data handling, stability, etc. Okay. So yeah, basically it's all theory, so I'm not going into all this detail. So yeah, I don't think anybody's attended today's class. Okay, so anyway, I'll just upload the problem sheet. Okay, so refer to the problem sheet and maybe try answering the questions. Okay, this is the problem sheet 4 for week 5. So there are 10 problems over here. So just open it in your system and try answering the questions. Maybe take 5-10 minutes to see, and then I'll come and we'll see what the answers are. Okay. Okay, so let us look at the problem sheet. Hollow cathode lamp used for the determination of an element. Four options. So what is the answer? Answer is it must contain the same element. Okay. HCl emits the element's sharp resonance lines, and the cathode is made of that element. Okay. So this is already we covered in the notes. Electrode-less discharge lamp is ideal for. So this I just found in the net. Okay. I could not find where sir has covered this part. So it's just like a factoid. So basically the explanation was that electrode-less discharge lamps give higher line intensity uh, for many elements with UV lines in below 200 nanometer, like for arsenic 193.7 nanometer, selenium 196, phosphorus 177.5, etc. So this like I just got it from the net. If the dissolved solid in the solution is high, total consumption burden is advantageous. Okay, we saw that in the class just now because uh, when the total solids is high, it blocks the premix furnace. Okay, but total consumption designs they tolerate the salts buildup because of their wider orifice. In AS, the high flame temperatures are operated at or are obtained at nitrous oxide acetylene flame. We saw it. It's used for uh, refractory element detection, and it can go to 3000 degrees Celsius. Alkaline earth metals are determined by AS in slightly reducing flames. Directly from the notes only. The quartz tube is used in the analysis of AS because it increases the path length. Because uh, if you increase the path length, it will boost the absorbance. Okay. When using a hollow cathode lamp as a source, the monochromator should have a spectral band pass of the order of 0.2 nanometer. So again, this I think sir covered in class. Okay. Next question is in a double beam AS, these are four options. So this is the answer. Okay. So this I asked you to do as homework. Okay. So yeah, just try to find out. EMTs are probably preferably used as detectors in AS because they ensure good signal to noise ratio. Okay. Advantage of automation is mainly through higher throughput or higher throughput. Why high throughput? Because automation in the form of auto samplers, programmed atomization cycles, ashing, drying, etc. It allows many samples to be run sequentially without operator input. Okay. EMT already told, high signal to noise ratio. Double beam AS modulation you have to learn. Most of them are directly from source notes, okay? I think this is it. Thank you. We'll just end the class.